Hello everyone, welcome back to another session for BMM2683 Applied Thermodynamics. In this session, we are going to continue our discussion about refrigeration cycle. Uh, as you have seen in previous session, we have started to discuss about the ideal vapor compression refrigeration cycle and also actual vapor compression refrigeration cycle. So in this session, we are going to solve two different examples for ideal vapor compression cycle and another example for the actual vapor compression refrigeration cycle. So here we have the instruction for example 1 for this chapter. We have a refrigerator which uses refrigerant 134A as the working flow, and it operates on an ideal vapor compression refrigeration cycle. And this refrigerator, this cycle actually is working between 0.14 and 0.8 megapascal. So we have minimum and maximum pressure in the cycle. If the mass flow rate of the refrigerant is 0.05 kilogram per second, we need to determine the rate of heat removal from refrigerated space, in other words, Q dot L, and also the power input to the compressor, or W dot, which is the required power for the compressor. And also we need to determine the rate of heat rejection to the environment, or QH or Q dot H actually, in form of rate. And also finally, we need to calculate the COP of this refrigerator, or coefficient of performance for this refrigerator. Now, let's see how we can find the answer for different parts of this question. Okay, first let's review what we know about the actual refrigeration. Okay, first let's see what we know about this cycle, or ideal vapor compression refrigeration cycle. The main components which we have in this ideal cycle are as what you can see in this figure. We have a compressor, evaporator, and also condenser. The QH, or the heat, is rejected in the condenser to the environment, and the QL, or heat, is absorbed by evaporator from the cold refrigerated space. And also we have compressor, which we need to power input to run the compressor. And the TS diagram for this uh, type of cycle also already is introduced to you, is like what you can see here. We have this dome which shows different phases of the uh, working fluid, which in our example here is R134A actually. And also we know that in state 1, which is the entrance of the compressor, we have saturated vapor. And also in state 3, which is the entrance of expansion valve, or the exit of the condenser, we have saturated liquid. Moreover, here we have more information about the pressures. We know that the cycle, or the ideal vapor compression refrigeration cycle, which we have here, is working between two different pressures. The minimum pressure is in the evaporator, or in the state 4 to 1, which is 0.14 megapascal, and the maximum pressure is for state 2 to 3. Actually, this process, for the process from state 2 to state 3, you know that this is the isobaric process actually, and pressure at state 2 and 3 are identical, and pressure at state 4 and 1 also is identical. So here pressure for this process, or for these two different states, is 0.14 megapascal, and pressure at state 2 and 3 is 0.8 megapascal. So with this information, now we can modify, or we can this graph actually, you need to know how to draw this graph. This is the general graph for an ideal vapor compression refrigeration cycle. So first, you need to know how to draw this graph, and also you need to know main components of this cycle. Then you need to go and find the other information which is required to solve this problem. The question, the different parts of the question means we need to find QL, WE, QH, and also COP, which is the ratio between the QL and WE. Here, to determine these three parameters, we need to know the change in the energy in the cycle in different processes. And you know that we need the change in these different processes is determined by the change in the enthalpy of the working fluid during these processes which we have in this cycle, which is already also discussed in previous session. To determine the enthalpies for different states, first we need to start with some assumptions. First of all, we need to assume that a steady operating condition exists, nothing changes with time in the cycle. And also, we need to ignore kinetic and potential energy changes in the cycle. In other words, the only changes in the energy of the system is due to the change in the enthalpy or internal energy of the system. So as you can see here, we have updated the graph which I showed you in previous slide, and I have already put the values of the pressures which we have. You can see here the pressure for this process is 0.8 megapascal, and for this process is from state 4 to state 1 is 0.14 megapascal, and W dot in, QL, and Q dot H. Now, to determine Q dot L, which in part A it is question to find Q dot L, W dot in as the power, and in part B we need to calculate Q dot H, and in part C we need to calculate COP of refrigerant. And as you know from the previous session, and also you can see in this graph, to find W dot in, Q dot H, or even Q dot L, we need to just understand how the energy is changed in this process based on the first law of thermodynamics. So Q dot L is equal to M dot H1 minus H1, enthalpy at this state, minus enthalpy at this state. M dot H1 minus H4. Why M dot? Because we are going to calculate Q dot L, or rate of heat transfer, or heat which is absorbed from the cold region or refrigerated area as the rate form. So we need to multiply this by M dot. Then you can see here, same for W dot in is actually W dot is in this process from state 1 to state 2, Q dot H from state 2 to state 3. In other words, M dot times H2 minus H3, and Q dot L is in this process. In other words, M dot H4 minus or H1 minus H4. So simply, M dot is given in terms of kilogram per second, is 0.05 kilogram per second. So to find Q dot L, W dot in, Q dot H, and also even in part C to find COP, or coefficient of performance for refrigerant. Here, we have refrigerant. If you remember, COP of refrigerant is desired output divided by the given input, which desired output for refrigerant, if you remember, is Q dot L, the heat, the amount of thermal energy which is absorbed from the refrigerated region. So if we have Q dot L and W dot in, we can simply calculate COP for this refrigerator. And to find Q dot L, W dot in and Q dot H, we need to have these enthalpies. So our problem actually is simplified to finding enthalpies or the thermodynamic properties for each one of these states. Now let's see how we can find these thermodynamic properties for these four different states. First, let's begin with the state 1. In state 1, we know how much is the pressure. Pressure is 0.14 megapascal. And also we know that in this state we have saturated vapor. So the enthalpy for this state should be enthalpy for saturated R134A as a refrigerant at this pressure. How we can find it? We need to refer to the thermodynamics tables which we have. The tables I have already copied from the textbook and pasted here, and you can see different tables which we have for this refrigerant. The working fluid in this example is R134A, and we have the tables, table A11, and for the saturated refrigerant, but uh, is it is the temperature table, and also we have the pressure table. What we have here is pressure. The pressure which we have here is 0.14 megapascal or 140 kilopascal. The table which we have here also is based on the kilopascal. So the pressure which we have here is 140 kilopascal or 0.14 megapascal. Then simply we can come to this table, and here we have enthalpies. Uh, we have enthalpies for this pressure, and you can see also here this is our pressure, and this is enthalpy for this pressure, enthalpy of the saturated liquid, enthalpy of the mixture or two-phase region FG, and also Hg, the enthalpy for saturated vapor. And as I told you, in state 1 we have saturated vapor. Then the enthalpy which we are looking for is here, Hg for this pressure, which is 239.19 kilojoule per kilogram. So simply we can find the enthalpy for this state. With the same procedure in the same table, we can also find the entropy uh, for these states. Entropy also is entropy of saturated vapor, which is at this pressure from same table, table A12. We can find entropy as well for this pressure. So we have already found the enthalpy and entropy for state 1. How about the state 2? In state 2, if you notice, we have a superheated, the state 2 actually is in the superheated region. So to find the enthalpy and other thermodynamic properties for this state, we need to refer to another table. Let's see what are the information which we have here. First of all, the pressure which we have here is 0.8 megapascal. It is given by question instruction. And the entropy is also equal to entropy which we have for state 1, constant entropy process in the compressor. So S2 is equal to S1, entropy at state 2 is equal to entropy at state 1, and also the pressure, we know this information, we have this information. So by this information, how we can find enthalpy for state 2? We know this is superheated region. So let's go to the table, and also you can check if state 2, first of all, we know this is in superheated region based on our knowledge about this ideal vapor compression refrigeration cycle. But also we can check it. How we can check this? The pressure which we have here is 0.8 megapascal or 800 kilopascal. This is the pressure. So let's see how much is entropy, because as I said here, we have also entropy. The entropy which we have here, S2 is equal to S1. So entropy is 0.94 almost. So entropy is 0.94. Okay. But the entropy which we have for this pressure at the state 2, okay, entropy is the last three columns. Here we can go to the last three columns and compare our entropy. This is our entropy S2. But at this uh, pressure, the entropy for saturated liquid, saturated and saturated vapor. Simply, we can compare the entropy which we have. We can compare entropy which we have with entropy which we have in the table for this pressure. As you can see here, the entropy for saturated vapor here is 0.91, but the entropy which we have here is 0.94. In other words, the state of the refrigerant at this state is superheated region, because the entropy S2 is bigger than the entropy for the saturated vapor. So by this, we can also check in which region is the state 2. Now we have checked and we understood that the state 2 is in the superheated region. So to find the enthalpy for this state, we need to refer to another table, which is superheated table for the refrigerant or working fluid, which we have here, R134A. Okay, now we have checked and understood that the state 2 is in superheated region. So to find the enthalpy for this state, we need to come to the table which represent the superheated, the thermodynamic properties for superheated refrigerant 134A. The pressure which we have is 0.8 megapascal. So in this table A13, we need to find this pressure. You can see here the pressure is here, 0.06 megapascal, and it increases here 0.40 megapascal until here is the 0.8 megapascal, the pressure which we have here. And also we have the uh, entropy for this state. The entropy, the amount of entropy for this state is equal to entropy for state 1. So it's 2 from, if you remember, state 2. For state 1, the entropy was equal to this 0.94, 467 kilojoule per kilogram Kelvin. So let's see. So S2 here is 0.94. I just have written here for myself. Okay, kilojoule per kilogram Kelvin. So we have entropy for this state as well. This is the pressure. So we need to compare the entropy which we have for this state with the entropy at different temperatures. As you can see here, the enthalpy in the superheated region change with the temperature as well. So the entropy which we have here is 0.94. Let's compare with this. Here you can see uh, the first, here is the entropy. This column represents the entropy, and as you can see here, for this pressure, the saturated temperature, the saturation temperature is uh, at the saturation temperature, which is 31.31 degrees Celsius, the entropy is 0.91. And the next uh, entropy actually is for 40 degrees Celsius temperature, and it is 0.9481. And if you notice here, our entropy is between these two entropy. S2 is between these two entropy. So it means the enthalpy for this state is also between these two enthalpies which we have. So our enthalpy is between these two. Is between 267.34 kilojoule per kilogram and 276.46 kilojoule per kilogram. How we can find the enthalpy for our state? We need to do interpolation. We have in enthalpy, we have entropy as well. The enthalpy which we have is 267.34 enthalpy at state 2 and enthalpy which we have here. How about entropy, which we have 0.9185. We have S2 here, 0.94 or 167. And also we have the entropy for this state, which is 9481. So we have all of this information, and we need to do interpolation to find H2. I'm not going to do this to show this process how to calculate it. It's already shown to you in previous example. Now let's see how after our calculation how much have been these enthalpy for state 2. After we have done the calculation, the enthalpy which we have found is 275.40 kilojoule per kilogram. If we do this interpolation, we can find the enthalpy for this state. And as you notice, we can also check H2 is between these two is 275, which is less than 276 and bigger than 267 kilojoule per kilogram. So by this, we have already calculated the enthalpy for state 2 as well. Now let's see how we can find the enthalpy for state 3. For state 3, again, we know that the pressure is 0.8 megapascal. This is one information which we have. The other information is, as you can see also here, and it is mentioned earlier, this state is on the saturated liquid line. So if we simply go to the table for saturated refrigerant or our 134A, we can find the enthalpy for this pressure 0.8 megapascal. We need to come to this table A12, and the pressure we have here 800 kilopascal or 0.80 megapascal, and you can see here we have enthalpy for different states. You can see here, and here is the enthalpies. These three are enthalpies. Here what we have is saturated liquid. It means we need to find HF for this pressure, which is 95.48 kilojoule per kilogram. As you can see, here actually. So simply we have already found the enthalpy for state 3. How about state 4? If you notice in state 4, the process which we have from state 3 to state 4 is throttling process in an expansion valve. If you remember from the thermodynamics, in the expansion valve as a steady flow throttling device actually, the enthalpy doesn't change, and in this expansion process, the enthalpy doesn't change due to the fast short time of the process, and due to the small heat transfer and so on. And we can assume that the enthalpy doesn't change in this process. So from state 3 to state 4, or in the expansion valve, we can assume that the H3 is approximately constant, and H4 in state 4 after expansion valve, no, state 4 and state 3, so it means state 3 to state 4, the process from state 3 to state 4 is in the expansion valve. We can assume that approximately the enthalpy for state 4 is equal to enthalpy at state 3, or H4 is approximately equal to H3. We have already calculated, we have already found the H3, so we have also H4. Now we have all of the enthalpies for different states in this cycle. As I told you, now we can use this equation Q dot L equal to m dot H1 minus H4 to calculate Q dot L as the rate of heat removal from the refrigerated space. And also we can use this equation W dot in to calculate the power input to the compressor. M dot H2 minus H1. We have H1, we have H4, we have H2 and H1 here. And M dot is given 0.05 kilogram per second. Simply, we can calculate the Q dot L and W dot. And similarly, we can calculate Q dot H by substitution of H2, H3, and M dot in this equation. As you can see here, we found this equation by evaluation of by investigation of the graph. So Q dot H can be calculated here as well, which is 9 kilowatts. However, we could also use this equation Q dot H equal to Q dot L plus W dot E. Here based on the first law of thermodynamics, says the energy cannot be destroyed or created. It just change only it can just come from one form to the other form, and you can see here Q dot L and W dot E come to our system, and Q dot H goes out of the system. So this is the only energy transfer to or from the system. So W dot in and Q dot L, which come to the system, should be equal to Q dot H, which goes out of the system. So we can use also this equation to find the Q dot H. And finally, the last part of the question, which is about the COP, or coefficient of performance, for this refrigerator is equal to Q dot L divided by W dot in. We have already calculated Q dot L and W dot in previous steps. Simply, if we substitute Q dot L, which is 7.19 kilowatt, divided by W dot in, 1.81 kilowatt, we can calculate the COP for this refrigerator, which is 3.97, or almost 4. And it means this refrigerator removes about 4 units of thermal energy from the refrigerated space for each unit of electric energy. In other words, it shows how much this refrigerator is efficient, and we can compare this refrigerator with other refrigerator by this COP. The next example will be for the actual vapor compression refrigeration cycle. Here we have another example for vapor compression refrigeration cycle, but this time we have an actual cycle, or actual vapor compression refrigeration cycle. In this cycle, refrigerant 134A enters the compressor of a refrigerator as a superheated vapor. So this is one of the information which we have, and also we know what is the refrigerant. So the pressure at the entrance of the compressor is 0.14 megapascal, and its temperature is negative 10 degrees Celsius. And the flow rate of this working fluid is 0.05 kilogram per second, and it leaves the compressor at 0.8 megapascal pressure and 50 degrees Celsius. The refrigerant is cooled in the condenser to 26 degrees Celsius and 0.72 megapascal pressure, and it is throttled to 0.50 megapascal. So you can see the one of the main difference between these examples, which is for actual vapor compression refrigeration cycle with the ideal one, is this information. We need to know more information to be able to solve that the problem or to evaluate that cycle. You can see we have temperature and pressure for different states or more states compared to the ideal cycle. Disregarding any heat transfer and pressure drops in the connecting lines, later we will see why this is important, between the components, we need to determine the rate of heat removal from the refrigerated space and the power input to the compressor, Q dot L here and also the W dot in. In part B, we need to determine the isentropic efficiency of the compressor. I have already discussed about that in previous session. We will see how we can calculate it in this example. And in part C, coefficient of performance for this refrigerator, or COPR for this refrigerator, should be calculated. First of all, if you remember, in the actual vapor compression refrigeration cycle, we have some differences compared to the ideal one. If you remember, for ideal one, we had just 4 main components and 4 main states were important for us. State 1, state 2, state 3, like this, state 1, state 2 here, state 3 here, and state 4 here, between the main components. But in a actual cycle, we need to have consider more states in the cycle, because in that case, for the actual cycle, we have heat transfer in the connection lines, we have the heat loss from the compressor, condenser, and pressure drop actually in the evaporator or in the condenser. So we need to also include those information, and the information also which is given here shows these pressure drops. And also you remember the TS diagram for this actual vapor compression refrigeration cycle. If you remember, we had this cycle. If we compare this with the ideal cycle, you can see in the ideal cycle, in the previous example you have seen already, state 1 was in this line on the saturated vapor line, and the state 3 was in the saturated liquid line. But now, or here is at the entrance of the compressor, and here is at the exit of the condenser. Now it is shown by state 4. And also, if you remember, for a state 4 to a state 5, we had some pressure drop and temperature drop due to the heat loss or heat transfer or pressure drop in the connection. What we have here is the pressure drop in the evaporator and condenser and also compressor, but not at the connection line. So the cycle which we have here, the TS diagram for this actual cycle which we have here, is something like this. But as you can see, we have again just 4 states, 4 main states, because we have ignored these, these pressure drops, which is just due to the connection pipes. So because it is mentioned that, and I told you that we disregard any heat transfer and pressure drop in the connecting line. So we ignored these pressure drops. So it will be like this. It is more or less similar to ideal cycle, but the difference is we will see how we can find it, but just to illustrate that, you can see state 1, it is not under saturated vapor line, and state 3, which is the uh, after condenser, is not on the saturated liquid line. And also the process, the compression process, is not isentropic in the compressor. Let's see how we can draw this graph. First of all, you know this red line, the dome for the uh, R134A, and now we need to find these four different states. The assumption to solve this problem, similar to the previous one, steady operating condition exists, and also we ignore the kinetic and potential energy changes. How to draw this TS diagram? First, we need to determine the state for each, the temperature and the entropy for each state. For state 1, we have the pressure. Pressure is given, P1 is 0.14 megapascal, and temperature also is given, negative 10 degrees Celsius. So we have pressure, we have temperature as well. So how we know in which region is it, and how we can find entropy for these state, and also how we can find the enthalpy for this state. We need to compare the values which we have here with the pressure and saturated temperature which we have for that pressure in the table. If we refer to the table which you have already seen here, saturated refrigerant 134A, the temperature table, for example, the temperature which is given, negative 10 degrees Celsius, the saturated pressure is 200 kilopascal. The pressure which we have here, is 0.14 megapascal, or only 140 kilopascal. So the pressure here which we have here is less than saturated pressure. In other words, it means that the P here is less than P saturation. So it means this state is in the superheated region. So now we need to refer to another table to find the enthalpy and entropy, which is superheated region. So in table A13, for the pressure and given temperature, the pressure is 0.14 and temperature is negative 10 degrees Celsius. So if we can simply come to this table and find the enthalpy for this state, 246.37. This is enthalpy for this state. Similarly, we need to go to the table for saturated refrigerant. First, we need to go to the table A12 or A11 to see and to check in which state is this, the state 2, in which region is this state. P2 is 0.8 megapascal, and T2, or temperature at state 2, is 50 degrees Celsius. Again, we can go to the table. The temperature is 50 degrees Celsius. So the temperature 50 degrees Celsius. 50 degrees Celsius. Let's find the here you can see we don't have that 50 degrees Celsius directly, so we can even use the pressure. The pressure is 0.8 or 800 kilopascal. The saturated temperature is 31.31 degree Celsius, but the temperature which we have here is 50 degrees Celsius. In other words, T which we have here is higher than the saturated for this pressure. So also this one means this state is in the superheated region. So to find the enthalpy for this state, again we need to refer to the superheated table. The pressure is 0.8 megapascal, temperature which we have is 50 degrees Celsius. Again, enthalpy we can simply find here 286.71. You can see here we have found in the table and written here H2 or enthalpy for state 2. How about state 3? For state 3, again we need to do same procedure. We need to go to the table A11 or even A12 and compare these pressure and temperature with the uh, saturated pressure and temperature. P3 here is 0.72 megapascal. So P3 for this table for the pressure 72 or 720 between these two. How about the temperature? Temperature which we have here is 26 degrees Celsius. Let's see if we have 26 degrees Celsius here. Yes, we have 26 degrees Celsius, and you can see saturated pressure is 685.84 kilopascal, and pressure which we have here is 120 kilopascal actually. We have two options now. As you can see here, pressure here is higher than the saturated pressure. In other words, it is, here P is higher than P saturated for the temperature, for this temperature, 26 degrees Celsius. This is in the opposite of the state 1. So it means it is in the uh, subcooled or the compressed liquid region. So we need to go to the table for the compressed liquid to find this property, the enthalpy or the other thermodynamics properties for this refrigerant or for this state. But also, if you notice here, the saturated uh, pressure and the pressure which we have here 720 kilopascal and the saturated pressure is about 600 something, 685, only 40 kilopascal is difference between them. So as an approximation we can use HF or saturated liquid enthalpy for state 3. You can see here it is just an approximation and we have some error in our calculation, but we can use that because it will not that much effective on the final result for our calculation. This is just for simplification. Otherwise, we need to go to the table for compressed liquid for the refrigerant. So H3 is approximately equal to the uh, enthalpy for the saturated liquid at this temperature. From the table A11 we can read this, and it is equal to 87.83 kilojoule per kilogram. How about enthalpy at the state 4? If you remember, state 4 enthalpy at the state 4 is equal to enthalpy at the state 3, because if we included the change in the system due to the heat transfer in the connection part, it would not be like this. But now, because from a state 3 to a state 4, we have only throttling and expansion valve, so it is similar to what we had for the ideal vapor compression refrigeration cycle. So the enthalpy for state 4 also is equal to enthalpy at the state 3, which is 87.83 kilojoule per kilogram. So you can see it is more or less similar to the previous example. We have already found the enthalpy for different states. The rest of that is similar to the previous example. Q dot L is equal to M dot H1 minus H4. This process, we have Q dot L, so changing the enthalpy because we have already ignored changing the energy due to the other changes in the system. And also, I have already discussed in the lecture, previous session, how we can find Q dot L from the cycle. It's based on the first law of thermodynamics. And we have already found this equation for this cycle. Q dot L equal to m dot H1 minus H4. M dot given H1 and H4. We have already found them here. Same for W dot in, which is in this process, m dot H2 minus H1, and we have H1 and H2. Simply we can calculate W dot in as well. In part B, we need to calculate the isentropic efficiency of the compressor. As I told you in the previous session, we can use this equation. The isentropic efficiency of the compressor is equal to entropy of the isentropic H2S, which is isentropic state actually. You know, if the compressor is isentropic, it means entropy is constant in the compressor. State 1 is before compressor, state 2 is after compressor. This is the actual compressor, which the compression process is not isentropic. We have pressure drop and we have the transfer in the compressor. But because we are interested also to calculate the isentropic efficiency of the compressor, we can assume that the compressor is isentropic. Then we will also have state 2s. State 2s has an interesting characteristics, and it is this which the entropy at state 2s is equal to entropy at state 1. This is based on this assumption. Now, to calculate the isentropic efficiency of the compressor, we need to use this equation, which it is already introduced in previous session, H2S minus H1 divided by H2 minus H1, which H1 and H2 already are for each stages, and H2S I told you is for this state. Now we have already found the H1 and H2. How about H2S? To find H2S, we know the entropy at this state is equal to entropy at state 1. And we know how much is entropy at state 1. And because, from the information which we have here, P1 and T1, we can refer to the table. The table for the superheated refrigerant, and we can find it, which is equal to 0.9724 kilojoule from this table. From this table for superheated refrigerant, we can find this information. We can find the entropy for state 1. So entropy for state 2s also is equal to that. And also we know that the pressure at this state is 0.8 megapascal. So for state 2s, we have temperature, we have pressure, and we have entropy. Then what we need to do is to find enthalpy for this state. How we can find it? We have the pressure, we have the entropy. Okay, let's see. The pressure is 800 kilopascal or 0.8 megapascal. It is here, and also the entropy is we have found entropy 0.9724. 0.9724. This is entropy for state 2s. So let's see here. This is entropy, and you can see here it is between these two. So by interpolation, similar to previous example, we can find the enthalpy for a state 2s by interpolation. This is between these two. These 2s, this is enthalpy. Our enthalpy is between these two. By interpolation, we can find enthalpy for state 2s, which is equal to 284.2 kilojoule per kilogram. So we have H2s as well. We have already found the H1 and H2. Simply we can calculate isentropic efficiency of the compressor, which is about 0.9 938 or 93.8%. The next part of the question is about the coefficient of performance of this refrigerator. Simply, you know that COP for the refrigerator, Q dot L divided by W dot in. And in previous step, we have already calculated Q dot L and also W dot in, 7.93 kilowatt divided by 2.02 kilowatt, which will be equal to 3.93 as the COP or coefficient of performance for the actual vapor compression refrigeration cycle. As you notice here, this is exactly same a cycle similar to the previous example, which was ideal cycle. But here, due to the irreversibility which we have in the compressor and evaporator, the COP is changed from 3.97 to 3.93. This is due to the change in the Q dot L and Q dot H. If you compare Q dot L and Q dot H here in these for the actual cycle with the ideal cycle in previous example, you will find out that the heat removal rate from the refrigerated space or Q dot L is increased about 10.3%. But in the same time, the power input to the compressor due to the irreversibility which we have in the compressor is decreased, and the decrease in actually this increase in the required input for the compressor is higher than increase in the Q dot L, which is 11.6%. So as you can see here, about 1.3%, the required input is increased for this whole cycle, and it is the reason to the reduction of the COP or the reduction of the efficiency of the actual cycle compared to the ideal cycle. By this, we reach end of this example.